Welcome everyone, and thank you for joining us today. In today's webinar, Dr. Marcelo Usseglio, Process Simulation Specialist at ProSimTech, will discuss the hidden aspects of enzymatic degumming. He studied chemical engineering at the National Technological University in Buenos Aires and received his PhD in engineering from the National University of La Plata. He is passionate about translating real-world renewable processes into simulation models to optimize and design processes, aiming to reduce both OpEx and CapEx. After 15 years of experience in vegetable oil refining, both in operations and engineering, he has developed rigorous process simulation models to be used in process optimization tasks. If you have any questions during the webinar, I ask that you please type them into the chat box on the right side of the screen. We will have time for Q&A after the presentation. With that, I'd like to say thank you, Marcelo, for presenting this webinar and sharing your knowledge with us. I'll turn it over to you now.
Okay, hi Dan and everyone. Thank you, Dan, for the introduction. And I want to also thank again to the AOCS team for inviting me to give this this second webinar that I hope you enjoy. And in this second webinar, and such as I told in episode 1, webinar 1, the core idea, or my core idea, is to show how information technology applied to process optimization through process simulation can bring us a high added value for process optimization tasks to reduce operative expenses, and finally to increase profit margin. And well, in this webinar, applied to degumming processes. Therefore, we will see the main characteristics of process simulation, its methodology, and the benefits of its application. But also, I'm going to explain some key theoretical concepts that I think that are important to mention, and that also, to be honest, nobody explains in congresses. So as introduction, I'm going to show some key theoretical concepts related to phospholipids, its chemistry, and the molecular structure. And then I'm going to explain how is used my process simulation models through two case studies. Okay, one is a PLC assisted water degumming, and the second one a PLA1 assisted acid degumming. Okay, so after a very short introduction to each enzymatic degumming processes, I am going to show how to properly diagnose each enzymatic process in terms of degummed oil composition, again mostly related to phospholipid composition, but also in terms of oil yield and operative expenses in each case study. Okay, by using, of course, the degumming simulation model for each case. Okay, just a very short introduction about ProSimTech. I'll try to do not repeat some slides about process simulation and so on that I already presented in the first webinar, because I think that those who are interested in knowing a bit more about simulation models and the methodology can also watch the webinar number 1. But I'm just going to mention some slides. But okay, about this short introduction about ProSimTech. ProSimTech is the first independent consulting firm specialized in process simulation software for vegetable oil refining processes and downstream related processes, okay, such as water, enzymatic, and acid degumming, the core topic of this webinar, but also neutralization, deodorization, physical refining with single or double scrubber, and different type of vacuum systems. Okay, But also I have developed process simulation models for tocopherol and omega-3 concentration processes, for fatty acid distillation, and also for biofuels production processes such as biodiesel production. And one interesting thing about all these simulation models is that all these simulation models run embedded in Excel. Okay, all these simulation model can be used within an Excel sheet, and of course we are going to see this in a couple of minutes, and all the results from the simulation model itself can be exported to different type of Excel sheets within the same file for further analysis. We are going to see how the simulation model works during the case, each of the case studies. So okay, just to put things into a context, typically in a commodity business such as vegetable oil commercialization, in which prices are fixed by international market, according to offer and demand and financial aspects, all the efforts of producers are needed to reduce OPEX. And I would say basically in terms of maximizing all yields, okay, trying to reduce energy consumption, mostly related to reduce steam consumption. The third key aspect I would say is to valorize the market price of co-products, okay, or byproducts, and finally to minimize the wastewater of the process, and all this with the final objective of increasing the profit margin of the operation. So within this context, process optimization tasks, as we see, are a must, okay, aiming to achieve all these objectives. And on the other hand, process simulation, I would say, is the best ally. Because first we need to diagnose the current processing scenario, okay, in terms of if we have to solve some issues during the processing of the vegetable oil, and then we need to analyze different type of processing scenarios, aiming to find the optimum processing scenario, and finally to run a test in the plant to achieve a given objective in terms of optimization. So this test in the plant allow us to verify the results from the results of our simulation studies. Okay. So the first question that probably arises here is, what is process modeling and simulation? And I would say that process modeling is the activity tending to represent an industrial process, okay? And basically by describing the fundamental phenomena that occurs in it. And this is done, such as we probably know, by means of mathematical equation. So this way, the equations are used to calculate properties of the compounds involved in our process, and to calculate the phenomena that take place in each of the unit operations that we have in our process. Okay, and so in a few words, process modeling is the tool to execute different kind of simulation studies, okay, in order to predict the impact in the process, in the actual process, and in the product quality, when we change the process variables, or if we change, for instance, the composition or or the mass flow rate of the inlet streams. So basically, I would say that we have 5 key building blocks to take into consideration when constructing a process model, and these are, of course, the compounds involved in our process, okay, the compounds properties, and normally the most important are the temperature dependent properties, okay, but also the basic in terms of molecular weight and so on. And of course, the type of process that we are going to study, first model and then to study. How to model each equipment of our process. And I have put this 5 key building block, which is to choose the appropriate thermodynamic model. And this is quite important, mostly when we have a given liquid vapor equilibrium. For instance, in a deodorization process. So once we have our process model constructed and validated against actual lab results and the actual process conditions, we can execute different type of simulation studies, aiming to, for instance, to predict the composition of outlet streams. I don't know, to predict, for instance, in the cases that we are going to see, the composition of the degummed oil, or to analyze and to verify the most convenient process conditions, okay, in terms of OPEX. We can do this as well with simulation model, and basically to comparing different processing scenarios within the using the simulation model. So basically, all these simulations and analysis give us, I would say, an in-depth knowledge about our process that many times it is not that easy to unveil in front of the plant, in front of the actual plant, only by following up the process variables of the process and with lab results. Okay. So, well, let us start with the core purpose of this webinar, okay, which is the application of process simulation in enzymatic degumming. And in this first case study that I am proposing to analyze, I'm going to show how to use the process simulation model for a case of a PLC assisted water degumming. Okay. And so in this case, I am considering the processing of crude soybean oil with about, I think, yeah, about 1,000 to 1,300 ppm of phosphorous, okay, related to the phospholipids content in this crude soybean oil. Also, I am considering, well, I missed the calcium composition related to the phospholipid salts. I am considering 44 ppm of calcium related to the phospholipids salts, and I have chosen a capacity of 1,000 tons per day, using 2% of water to perform the hydration of the phospholipids, and using 200 ppm of enzyme. Okay. So for this case, my idea is to evaluate and to calculate with high degree of accuracy oil losses related to the phospholipid profile found in the crude soybean oil. Okay, then to calculate the glyceride increase, which is related to the action in this case of the PLC enzyme, and in a way is an indicator of the activity of the PLC enzyme in this type of enzymatic degumming process. But also is an indicator of oil saving. Which is in fact the OPEX driver to choose this type of degumming. And finally, I would like to show how it is feasible to quantify and to assess if our current processing scenario or our current processing scenario is running under expected values related to the action of the PLC enzyme. Okay, let us consider a typical process flow diagram of the PLC assisted water degumming. Okay, I am not going to explain in very detail in all the detail of this process, because this kind of information you can find it quite easy surfing the web or even contacting the technology companies. But I'm just going to at least mention some key aspects. Okay, so in this typical process flow diagram, we have a first heat exchanger strain, okay, with a economizer and a cooler. This is to get the appropriate temperature for the enzyme action. And then we have the enzyme and hydration water reactor, okay, which also act as a conducting time vessel for both the enzyme and the water that we need to use to get to get the hydration process to occur properly. And finally, we have a heating stage, okay, to get the appropriate temperature prior entering to the centrifuge to remove the phospholipids with the water phase, okay, and to send the degummed oil to further refine, okay. So from the point of view of this process and the compounds that we want to remove, the phospholipids are emulsifiers, okay, that cause in a way losses of oil during the traditional, I would say, water degumming process, and particularly when we are separating the oil phase from the water phase, in which we are also removing the gums. Okay, so one of the main characteristics of the phospholipids is that act as emulsifiers, and this property in terms of the processing means that we are linking some oil fraction to this phospholipids that we are removing with the water phase, and in a way this is a loss. This is an oil loss. Okay, so in this slide I have put those phospholipids I would say typically found in soybean oil. Okay, so these are the phosphatidyl ethanol amine, okay, the phosphatidylcholine, the phosphatidylic acid, and the phosphatidyl inositol. Okay, but also and this is the distribution, or I would say that the composition of these different phospholipid that we can find in the crude soybean oil. Okay, but also we also have the calcium and magnesium salts. Okay, and these salts mostly are related to phosphatidic acid and to a lesser extent to phosphatidylethanolamine and to phosphatidylcholine. Okay, so we have calcium and magnesium salt of mostly phosphatidic acid and to a lesser extent to phosphatidylethanolamine and phosphatidylcholine. During the next slide, I'm going to refer, probably you are going to hear me to mention, not to from the full name, but I'm going to probably mention PA and PE and PC, just because it's a typical name and are the, I would say the initials that that are used in our market. Okay, so and typically in crude soybean oil, typically the crude soybean oil has a phospholipid content range of 2% to 2.9%. Okay, depending on the process upstream of the degumming, of the water degumming process. Okay, used to extract the oil from the bean. So this is the composition, but as we already know, we typically express the phospholipids content in oil as phosphorus content. Okay, we typically express analyzing the phosphorus content in the crude soybean oil. So if we express the phospholipid content, but now as phosphorus content, we are going to find that we have about 850 to 1,200 ppm of phosphorus. Okay. Well, so the first question is why we use phosphorus content. At least is one of the questions that I typically ask to myself. Okay, so I would say that we use to express phospholipids content as phosphorus content to follow up the degumming process. Okay, either in a water degumming or in a enzymatic degumming or even in a acid degumming used in the chemical refining route. And I would say and this is because it is a quick and cost-effective analysis. Okay, if we compare the complete analysis required to measure the phospholipid content as phospholipids, and even to express it in the different phospholipid species. So I would say that in terms of quality, this phosphorus analysis is a parameter to comply a given oil specification. Okay, either along the refining process or even to sell a given degummed soybean oil. Okay, so we use this analysis about phosphorus content, but also in terms of total oil losses, we use it since it is a way to control the performance of the oil. Okay, it is a way to control the performance along the entire degumming or along the entire refining processes. And the thing is here that for this purpose, then we need to reconvert the phosphorus content to phospholipids content. Since, as we know, the phospholipids content are the actual compounds that we are removing from the oil. Okay, and why? Because we typically need to check the global oil losses, and to do this we need to know the fraction of phospholipids, okay, that we are removing, but expressed as phospholipids. And so for this, such as probably you already know, we like to use a conversion, okay, a conversion number to simplify this conversion of expressing phosphorus content to phospholipid content, or the other way around. So we typically have a magical number to do this. Okay, that's, I could say that sometimes many people doesn't know or understand where it comes from. Okay, which is in fact this conversion ratio. Okay, so this number, I would say, this magical number is sometimes provided by oil process technologies. Okay, toward to calculate oil losses during water degumming or even in chemical refining and acid degumming. Okay, by using a given performance formula, which then this value as the result of using this formula gives some guarantees values. Okay, and we typically use to convert phosphorus content in ppm to phospholipids in ppm content a number or a ratio of 30. Okay, and without knowing exactly why. Okay, this conversion ratio or formula, okay, is the one I have put in this slide, which relates the mean phospholipids weight and the phosphorus atomic weight. Okay, is this number. Okay, so this conversion ratio, in a way, is expressing this number. Okay, I have also put this table, okay, in which we can see the molecular weight in this column, okay, and the different type of phospholipids. Okay, those free phospholipids and those phospholipids that are forming a salt with calcium. Okay, and such as we see this ratio, okay, in general, or at least for those phospholipids not linked to a salt, this ratio is much lower, okay, than 30, and only those salts has a little bit higher value than 30. Okay, and the phosphorus atomic weight I have put here is about 31. Okay. So I would say that 30 is a high value to use it for process performance. Okay, since it overestimates the actual performance, but that we should really have, or we should really test it. And in some cases, this overestimation is about 20% high. Okay, so let us see. Let us see some examples. Okay, so I have put this table here just to mention that this strategy changes along the process. Okay, since the composition of phospholipids changes along the degumming or along the refining process, and this depends on the type of vegetable oil and on the type of process. For instance, in the case of crude soybean oil. For the composition of phospholipids in the oil that I have put here. Okay. The ratio is around 20, 25. Okay, 5 points below this 30 value that we typically use when we convert phosphorus content to phospholipid content, and then to measure theoretically the global oil losses that we are analyzing in our process. And now, if we see the ratio for water degummed, okay, it's around 26.8. Since we have a higher concentration of phospholipid salts, okay, than before. But well, anyway, the number is still below 30. And now, if we see the same ratio, but for a fully enzymatic degummed oil, the ratio is below 20. Okay, I would say it's the lowest value, and this is because now we have less of phospholipids, okay, which have a much lower molecular weight. And let me come back. Okay, so in a fully degummed enzymatic degummed oil, we have less of phospholipids, and such as we see, the molecular weight, okay, are much lower than the original phospholipids. Okay. Okay, this slide, just the purpose of this slide is to let you understand that if we want to accurately measure our global oil losses against a theoretical value, we need to take into account at least once the real phospholipid composition of our oil, and then to convert, if we are going to use a given conversion ratio, to a value that it is related to this composition, and not always to use this 30 number. Okay. Well, let us go to the process itself and the PLC action. So, such as we know, regarding the PLC action, the action of the enzyme PLC is that of the cleaving ester phosphate bond here, okay, and here, and it has also a given specificity of escission towards to PE, okay, and BC. Typically, I know that nowadays DSM is commercializing some cocktail of two different PLC that also attacked this ester bond, but the typical PLC has selectivity action to PE and to BC. Okay, so so the reaction, okay, in this case I have put the PC. So we know that PC is the most hydrotable phospholipid and has the highest emulsification, okay, strength, I would say. So the PLC enzyme react with PC, forming a diglyceride, and a phosphate related to the phospholipid in which the PLC enzyme acted. And this new species of, let us call it phospholipid, but it's phosphate, has a much lower emulsion. So what we are going to achieve here is a much lower loss of oil due to emulsifying effect, and then we are going to have a certain gain in terms of deglyceride from the phospholipid in which the enzyme is acting. Okay, so in a way, this is an addition of oil gain. So here we can see the chemical structure of PC. Okay, so with this fraction of chemical structure, which is strongly soluble in oil phase, which correspond to the deglyceride part. We also have the phosphate fraction of the compound, which is strongly soluble in water. So one, okay. So this big part of the structure of the chemical structure is quite soluble in oil phase, okay? And this part of the molecule is soluble in water. So as we saw, the PLC enzyme is act on the ester bond position 3, in which the phosphate ester is linked to the phospholipid. Okay. So this way, and after the enzymatic reaction, we have as reaction products a deglyceride, okay, and a choline phosphate. And we clearly see that the original phospholipid choline is split practically, you can say, in two new compounds, the phosphate choline and a deglyceride, which each of these are respectively soluble in water and soluble in oil. So let us now discuss the process and then the simulation model. So particularly in this case of running a PLC enzymatic degumming, and since we need to make a follow-up of the process, of the performance of the process, we are interested in knowing how is the total oil loss, okay, calculated in a conventional water degumming. I mean, in a water degumming without using the PLC enzyme. And how is the phosphorus concentration related to the phospholipid concentration? And how do I measure the gain in terms of oil when using the PLC enzyme? Okay, so a viable approach when evaluating the performance in enzymatic degumming is comparing the total loss against the total loss that would have in a conventional degumming. So in the case of the PLC enzymatic degumming, we know that a measure of saving, such as I mentioned it before, in terms of less oil losses versus the oil losses in a conventional water degumming, is the increase of deglyceride before and after the action of enzyme. Okay, and I would say related to the PCMPE composition. Also the output composition, the effectiveness of the enzyme, and to have a given measure of a lower emulsifying effect of the phosphates that we are in a way producing. So we need to also have a theoretical way to compare the actual increase of the glyceride in our actual process due to the action of the PL enzyme on PCMP. And of course an appropriate and accurate way to compare it. So let us see now the example. Okay, so I'm going to switch to the simulation model. So in this is a simulation model, and in this first sheet we have the simulation model itself. okay, which is based on the PLC enzymatic degumming flow diagram that I have shown in the other slides. And such as I was explaining before, in terms of the simulation, it is important to characterize the oil as realistically as possible, okay, and mostly in terms of the compounds, and in this case, in terms of the phospholipids that we have in the crude soybean oil. Okay, so here we see the first exchanger train with the economizer and the cooler. Here we see the enzymatic reactor, okay, the enzyme addition and the water addition also here, the enzyme addition, and here we see the centrifuge in where we perform the separation of oil phase and water phase. Well, and here we have the vacuum system, okay, and this is the composite. If I double click in this stream, I display the composition of the crude soybean oil that I am considering. Okay, probably you cannot watch it too clear, so I'm going to try to put some stream table here. Sorry. It's not this one. Here. Okay. Okay. Sorry, but just you can see now better than before. I have here we have the composition of this crude soybean oil in terms of free fatty acids, in terms of tocopherol, triglyceride, diglyceride, but also in terms of the phospholipids, those that are free, but also those that are linked, forming a salt. Okay, and this is important because we are going to analyze the performance of the enzyme action. Okay. And in these other sheets of this file, we have all the results imported from this simulation run. Okay, and here we can analyze a very detail of the result from the simulation. Okay, so this last run of the model simulation, okay, let us say it has the results with the plant running with the appropriate performance of the enzyme. Okay, so here we can see, for instance, that we have a given increase in diglyceride content before, okay, in the crude soybean oil and in the water gum, from 0.5 mass percent to about 1.5 mass percent. So this is this indicator that we are going to follow, or we are going to check in our process, if we have our process running properly. Okay, but now we are going to analyze a given, or I would say some hypothetical situation. Okay, I'm going to come back to the presentation. Okay. Okay. And so let us consider that we have a given reduction, okay, of the enzyme reaction. Okay, we typically the conversion of the PLC acting on P and PC is about 85%. Okay, now let us consider that we have a given decrease of this conversion, okay, from 85, which is the value that I have now in the model, and now we have a reduction of this conversion, okay, from 85% to 75%. Okay, and let us say that the problems this is because of some problem with the dynamic mixer that we are using in the plant to mix properly the enzyme with the soybean oil, or for instance, where we have some lower activity of the enzyme due to a high temperature exposure during storage. So what we are going to analyze is how sensitive is the decrease in terms of phosphorus, okay, expressed in parts per million in ppm in the final degummed oil, and how sensitive is this impact in the increase of diglyceride in the oil before and after, okay, mostly in the degummed oil. And we are going to analyze the impact on operating cost. Okay, so I'm going to switch again to the simulation model. Deeply sorry, because I think that I am exceeding the time that I thought. It's supposed to, but okay. Here I'm changing the conversion, okay, from 85 to 75%. Okay, so every time I change something in the simulation model, okay, of course I have to solve again all the equation, and this is by clicking in flowsheet and then solve. So now all the equations. Well, this was quite quick because I just changed the conversion. So let us now see. Let us now see what happened in terms of diglyceride and in terms of phosphorus content in the water degummed oil. Okay. Before I update the calculation, we have about 54 content expressed as phosphorus and in ppm. Okay, and we have an increase from 0.5% to 1.5%, okay, of diglyceride. So I'm going to update all the results, mainly to check these indicators, okay, because all of this is tended to analyze if we are facing this problem, okay, in the plant, and we are using the simulation model to properly diagnose where is the problem and why we have this reduction in terms of diglyceride. Okay, to update the calculate to update sometimes takes a time. Okay, let us see first. Okay, what happened here? It didn't change that much, I would say. Yeah. Let me check again. Yeah, well, let us reduce a bit more. Okay. Okay. Okay, it's supposed that this value should reduce because I am reducing the action of the enzyme. Yes, okay. We have a bit less, I would say, diglyceride content than before. Okay. Now we have a value a little bit lower than that 1.5%. Okay, I expected a lower value, but okay. So let us see now in terms of phosphorus. In terms of phosphorus, again, it didn't change that much. Okay, the former value was 54 ppm express of phosphorus again, and now we have 55. But now let us check the new situation in terms of operative expenses. Okay, in this first column, I have put the expenses of the process. Okay, in terms of the OPEX per ton of crude oil processed. Okay, this is the expenses due to the oil losses, and finally, this is the sum of both numbers. And here we have the income from byproduct cell, okay, which in this case are the gums. And finally, I have put the situation comparing both simulations. So I'm going to click here to put all the new values in this second column, which represents all the values from the second simulation run, in which I have decreased the action of the enzyme. So such as we see here, we have a lower conversion to diglyceride of the enzyme action, since we have now a lower performance of the enzyme. It is not significant in terms of diglyceride, okay? We have a little bit more gums produced, since we have a lower action of the enzyme, and this diglyceride that we are not converting remains in the phospholipids. Okay, so if we express this in terms of less diglyceride conversion, which means into a lower oil loss, okay, here, because we have a lower overall efficiency. Now we have an increase of the OPEX of about $20,000 per month. Okay, so this is a lot, and we are just comparing the potential oil gain that we would have if we have a proper action of the enzyme. Okay. I'm going to come back to the presentation. Sorry, Dan. How about the time? Can I continue or?
Hi. Yeah. You can go over a little bit. That's okay.
Okay. Great. Deeply sorry, because I think much more time than expected. Okay. Now this is case study 2. Okay, and in this second case study, which is quite similar to case 1, the former case that we saw. But now in terms of how to use the simulation model, what and how analyze, but now apply to a PLA1 assisted acid degumming. Okay, so we are going to see again the phospholipid follow-up to determine oil loss, how to calculate in this case the theoretical free fatty acid increase according to the phospholipid profile and content in the degummed soybean oil, and of course according to the enzyme performance, and finally an operative comparative analysis when we face some problems again with the enzyme dosification. Okay, so again, I'm going to consider I'm considering a typical PLA1 assisted acid degumming, such as the one I am indicating here, and in which we can identify again the inlet heating stage, the acid solution injection, the mixing, the cooling, the enzyme dosification, the reactor, the enzymatic reactor, the heating that we need prior to the centrifuge, the centrifuge in which we separate the oil phase and the water phase with the phospholipids. Okay, and we know that in this case the enzyme converts both hydratable and non-hydratable phospholipids into lysogams, okay, into lysophospholipids and free fatty acids as a result of the reaction. And the good thing of this reaction again is that the lysogams or the lysophospholipids are more hydrophilic than the original phospholipid, which makes them easier to remove from the oil during the separation inside the centrifuge. So regarding the non-hydratable phospholipids, we know that this type of compounds are not easy to be removed, only contacting them with water. Okay, and let us see why. Sorry. So this is the chemical structure of the phosphatidic salt, of the calcium phosphatidic salt proposed by Albert Histra. Okay, I have put the source of this information in the footnote of the slide. So basically, he proposed that since we have a different charges of the salt cation, in the phospholipid structure, which is linked to the calcium, okay, then a fatty acid anion with a charge, a minus charge 1, okay, is linked to this phospholipid salt, okay, forming this phospholipid, this new phospholipid structure, I would say, which is bonded to a free fatty acid with a -1 charge. Okay, so this way we have, I would say, 3 molecular chains which are strongly soluble in oil loss. Okay, this one, and this one, and this make not easily to be reached. This make that the water part, the part that is soluble in water is not easy. It's not easy to be reached by water. Okay, and I would say practically impossible to be removed the phospholipids from the oil only using water, and that is why we use acid. Okay, so here in this slide, I have put citric acid, which is one of the typical acid reactions that we use to cut, okay, this bond. And basically this reaction is a cationic exchange reaction. Okay, so what we are doing here is to use a stronger acid, which is the citric acid here. It could also we can also use phosphoric acid, but here we are using, because typically in enzymatic degumming we use citric acid. And so since the citric acid is a stronger acid than the fatty acids, okay, allows to release the cation calcium, okay, from the acid, from the free fatty acid. Okay, so what we basically have due to the reaction, okay, and here we see how is the asymmetrical reaction between the calcium phosphatidyl salt with the citric acid, and what we need. So basically, we are going to form calcium citrate, okay, which is a precipitate, and so we in this reaction, 3 molecules of calcium phosphatidic salt react with 2 molecules of citric acid to form 3 phosphatidic acid, 3 free phosphatidic acid, our precipitate of calcium citrate, and 3 free fatty acids. Okay, this is the typical reaction when we use citric acid, of course, taking into account this chemical structure. So we have converted, okay, on one hand, a calcium citrate, okay, which is strongly, which precipitates, okay. This is important to mention, and we have this oil that is not linked anymore to the phospholipids and is oil soluble, and then we have our typical phosphatidic acid, which now are much more easily to be removed with water. Okay. So what we have now, yeah, okay. Let us now to analyze the reaction of the PLA1. Okay, such as we probably know, the PLA1 reaction is acting on the ester bond of position 1 of the phospholipid, okay, and is releasing a free fatty acid, okay, and forming a lysophosphatidic acid, in this case that I am considering a phosphatidic acid. And in terms of the process, the good thing is that this new type of phospholipids, the lysophosphatidic acid, is much more soluble in water, okay, and of course it has a less emulsifying effect of oil and water. So basically we are going to reduce the emulsifying effect, and then the oil losses to the water phase, and in a way we have a gain of free fatty acid in the oil. And this is basically good because in a way we are reducing the volume of gums that we are separating from soybean oil that we are processing, and in about a third part of the original chemical structure. Okay. And the good thing is that, such as we already know, the market price of gums are much lower than the market price of the distillate that we can produce eventually in a deodorizer or in a physical refining process. Okay. Now I'm going to switch to the simulation model of this PLA1 process. First, going to close this one. And I'm going to open the second one. Such as you see, this is an Excel sheet. And, well, we have all the complexity of the simulation model within an Excel sheet. So this is the simulation model of the PLA assisted acid degumming, okay, that we saw in the former flow diagram, but now in this simulation model. Okay, I'm going to change this. I'm going to run the simulation model, and again, we have the composition of the soybean. In this case, the water degum oil entering to the PLA1 enzymatic degum process. Going to insert an external report to allow you to see the composition. Okay, so again, it is very important to properly characterize, in terms of the calculations of the simulation model, the composition of the soybean oil that we are going to process. So again, we have sorry, Dan, you are hearing me, right?
Yes, I can hear you.
Okay, because I think I am facing some connection cuts. Okay. So again, in this model, we have a simplified flow diagram to import all the results from the simulation model. Okay, and we have some much more detail of the results, and again we can compare the operative expenses of two different simulation studies. So I'm going to come back to the presentation. So let us now consider that we are processing. Let us say, we are processing a soybean oil, okay, a water degum soybean oil, okay, with the same phospholipid composition, okay, than the composition that I have considered in the simulation model. But now we have a decrease in conversion reaction in both reactions, okay, in the acid reaction and in the acid reaction, we are going to have a decrease from 90%, which is the typical conversion of the acid reaction using citric acid, to 80%, and we have a reduction from the typical conversion reaction of the PLA1 from 95% to 70%. Okay, and again, the problems or the probable causes of this are problems with both dynamic mixers. Okay, let us say that the motor of these dynamic mixers suddenly stop, or that we have a lower activity of the PLE1 enzyme due to a higher temperature exposure during storage. Okay, and again, we are going to analyze how sensitive is this problem, okay, in terms of the decrease of the phosphorus or the phospholipid that we are removing in the full enzymatically degummed oil. We are going to analyze what happens or the impact in terms of the free fatty acid release due to the action of the enzyme in the phospholipids. Okay, and finally we are going to analyze the impact on operative cost. Okay, so going to come back again to the simulation model. So basically what we are analyzing here is that we are using exactly the same amount of enzyme, okay, but we are facing some problems, either with the dynamic mixer that we typically need to use in the process, this one or this one, okay, and we are using exactly the same amount of citric acid. Okay, so we are going to have on one hand some a lower transformation of those salts into those phospholipids that are feasible to be hydratable, and we are going to have a problem with the enzyme acting on the phospholipids to make them less emulsifying effect on the oil. Okay, so what I'm going to do is go here, and I'm going to change, okay, the conversion of the street reaction on the salts from 90 to I think from 90 to 80. And in the case of the enzymatic reactor, I'm going to change from 95 to 70. So okay. So since I change some input information of the model, go here and click on solve. Now the model is running. Sometimes depending on the change, it takes a while. I hope this is going to be. Let us see if we can. Okay, if this takes too much time, I'm going to show the result directly from my presentation. The thing is that inside or behind this simulation model, and such as I was explaining in the first slides, we have all the equations and all the basically the equations to calculate the properties of all these compounds that I have shown here in this table, and all the equations involved in each of these unit operations. Okay, so we are talking about, I would say, thousands of equations, and well, it takes some time to converge all the results of each of these equations. And probably now that so every time a given stream or a given equipment change from black to yellow means that the equations involved in that stream or in that equipment are running. Okay, so as I said before, since I am reducing the conversion of the acid reaction and the conversion of the enzymatic reaction, we should see now a higher content of phospholipids in the fully degummed oil. Okay, and we should see now a lower content of free fatty acids in also in the degummed oil. And this is not good because we are trying to remove or at least to produce some free fatty acid due to the action of the enzyme of the PLA1 enzyme on the phospholipids. Okay, this is taking too much time. I think I'm going to change directly to my presentation. Yeah. So basically, these are the results. Okay, so due to the lower reaction conversion of both acid reaction and enzymatic, we have a higher production of gums. Okay, a lower free fatty acid concentration in the full degummed, which is not good because we are expecting to produce or to translate gums into distillates. So this is not good, and we have a little bit higher residual phospholipid content than before in the full degummed oil. Okay, so basically now we have higher losses. Okay, this here is expressed in dollars per ton. Okay, and for a capacity of 500 ton per day, this means that we have a lower gain than in the appropriate processing scenario of about $3,000 per month. Okay, this is in, and if we annualize this number, it's about 30,000 per year, which is a lot. Okay, which is a lot because we are the thing of using an enzyme is specifically to get some gain in terms of less emulsifying effect of the phospholipids, since we are converting into a lysophospholipids, and to have a certain gain in free fatty acid. I'm going to come back just to check. Yeah, now the. But okay, this is exactly the same. Okay. Okay, guys, this was it. Deeply sorry because I have extended by far the typical 45 minutes that I should use. But okay, I think.
Hey, Marcelo, we have a question. What methods or techniques are used at the plant for oil characterization?
Sorry, again, what method or techniques?
What methods or techniques are used at the plant for oil characterization?
Okay. To be honest, I am not a lab analyst specialist because I think the question is related to what type of method are used in the plant. Frankly speaking, I do not know them. What are those?
Okay, we have another question here. Before using the simulation, is it necessary to know exactly the amounts of all the phospholipids?
Yeah, at least once, I would say. At least since to perform phospholipids analysis, I don't know, every day or every month, it is sort of cost consuming and also time consuming. I would say that at least we need to know the actual composition in terms of phospholipids that we for the typical soybean oil or rapeseed oil that we typically process. And what with this composition, then we can use it as an input information for the simulation model, since it is relevant to know the composition of phospholipids. Okay.
Well, thank you, Marcelo. I don't see any more questions.
Thank you.
So,
thank you. Anyway, if someone of you need or would like to ask a new question, you can send me by email. No problem. Okay.
All right. Well, thank you. I'm going to conclude the webinar now. Have a good day.
Have a good day, you too.